Hello everyone. Welcome to assignment number 2 on electrical machines 1. This is based on the transformer. In the first numerical, a 100 kVA 2000 volt by 200 volt 50 Hz distribution transformer has core loss of 500 watt at rated voltage and copper loss of 1200 watt at full load. It has following load cycle. So percentage load cycle, power factor and hours are given. 0% load, no need to power factor as there is no load. So 3 hours for no load. 50% power factor is unity, 6 hours. 75% load, 0.8 lakh power factor, 8 hours. 100% loading, 0.85 power factor lagging, 5 hours. 110% load, that is overload, power factor is unity, and hours are 2. So here what is the data given? Rating of the transformer is given as 100 kVA. Copper losses are 1200. Full load copper losses are 1200 watt, that is 1.2 kW, and the iron losses are 500, that is core losses has a 500, that is zero point 0.5 kilowatt. Why I am converting into kilowatt? Because I need the energy calculations in kilo form. Again, S is in terms of K, so I am bringing all the power in terms of K only. So kVA, kW, kW. So we will prepare a table. Let load is taken as a factor N, power factor is recorded here, working hours are recorded here, and I'm going to calculate the output energy from the transformer. So output energy is equal to N into rating, which is in kVA, N into S cos phi into number of working hours, kWh. So kilowatt, Ns cos phi is the power in kilowatt into number of working hours. Iron loss is nothing but number of hours into iron loss. Though the load is present or not present, iron loss is continuously taking place, that is core losses are continuously there, so it is multiplied by hour. Copper losses, number of hours of working into n square. N square is a loading condition into PC. Why it is n square? Because copper losses are square proportional to the current in the and current is depending upon loading condition. So in the first, for a 0% load, power factor is not required, so working hours are 3 hours. So output energy, as there is no power factor and load is 0%, this factor output energy is 0, but still this 3 into 0.5 will give you 1.5 kW is the iron loss taking place, though there is a no load. Obviously there is a no load means N is equal to 0, hence no copper loss is there. Likewise for 50% load, unity power factor and 6-hour working, so N is equal to 0.5, S is equal to 100, cos phi is equal to 1, and number of hours is equal to 6. So it gives you 300 kilowatt hour. Iron losses, 0.5 into number of working hours are 6, so it is 3. So like, and copper losses, number of working hours are 6 into zero point 0.5 square into 1.2, it gives you 1.8. Likewise for all loading condition, this table is completed. Now I will make the total. So for output energy, so I will make the summation of this output energy for a 24 hour. This is a total 24 hours. So for one day I am making the addition, so it gives you 1425 kWh, 1425 kWh. Iron losses are 12 kW and copper losses are 16.104 kW. So how will calculate all day efficiency? All day efficiency is equal to output energy in a day divided by output energy in a day into 100. So output energy is 1425. So 1425. How we'll calculate input? Input is equal to output plus losses. So output energy in a day plus energy losses, that is 1425 plus 12 plus 16.104, it is the total iron plus copper losses. So it is taken addition into 100. If we calculate it, efficiency is 98.06%. Let's prepare next example. In this, transformer is of 100 kVA, 50 hertz, 400 by 11,000 volt single phase transformer has efficiency of 98.5 when supplying full load current at 0.8 power factor lagging and 99% when supplying half load current at unity power factor. Find the core and copper losses, and at what values the load current is max current, the maximum efficiency will occur. So there are two types of calculation. We have to calculate the core and copper losses. Now efficiencies are given, we have to calculate the core and copper losses, and maximum, at the maximum efficiency, what will be the load current, that is to be calculated. So what is the formula of efficiency of transformer? Efficiency of the transformer is equal to N into SFL cos phi. N is the percentage loading, N is the loading in per unit, SFL is the full load rating of the transformer, cos phi, divided by N SFL cos phi plus Pi plus N square copper losses at the full load condition. So if I rearrange this equation, I will bring this eta in this side and I will bring this equation transfer on this side, and again transferring this on this side. So if I rearrange this equation, Pi plus N square PCU full load is equal to N SFL cos phi is equal to 1 upon eta minus 1. So in the case 1, what is the efficiency given? 98.5%. Full load current is at the full load current, means S is equal to 100 kVA, loading condition is full load, so it is N is equal to 1, cos phi is equal to 0.8 power factor lagging. At that time efficiency is 98.5, that is 0.985. So substituting this value in this equation, N is equal to 1, power factor cos phi is equal to 0.8, and S is equal to 100 kVA, that is 100 into 10 raised to 3. So I will get Pi plus PCU full load is equal to 1218.24. Similarly, in case 2, 99% efficiency supplying a half load. So S is equal to 100 kVA, N is equal to 0.5, cos phi is equal to 1, cos power factor is given as a unity, and efficiency is 99%, that is 0.99. So substituting N is equal to 0.5 in this equation, N is equal to 0.5, SFL is 100 kVA still, cos phi is the unity, 1 upon point eta, in this case efficiency is equal to 0.99 minus 1. So second equation is Pi plus 0.25 PCUFL will 50505. So we got a two simultaneous equation. This is equation number 1, this is equation number 2. Solving these two equation, I will get the iron losses as the 267.4 watt and copper losses at the full load is 950.6 watt. So I want to calculate the current at the maximum efficiency. For that I require full load secondary side current. So full load secondary side current is equal to rating of transformer divided by voltage at the secondary, S divided by V2. So 100 into 10 raised to 3 divided by voltage at the secondary is 11,000, sorry. So 11,000 is equal to this current, full load current is 9.091 ampere. So how will calculate the current at maximum efficiency? There is a formula at current at maximum efficiency, I2M is equal to I2 full load under root Pi divided by PCU full load. Same formula is for calculating the kVA rating at the maximum efficiency. I is replaced by S. S2M is equal to S2 full load under, or SM is equal to S full load under root Pi divided by PCU. Same formula is applicable for current. S is replaced by the current. So I2M, so I2FL is here 9.091 under root Pi and PCU substituted. So I got the current 4.821 ampere. When the current is equal to 4.821 ampere, the efficiency will be maximum in the transformer. So this is the end of the second problem. So let's solve the third problem. In open circuit and short circuit test, results are given. So open circuit test is performed on the LV side and short circuit test is performed on the HV side. Okay, so we have to determine the efficiency and approximate regulation of transformer at full load 0.9 power factor lagging. So we will see this condition later. So first, from the OC test always give you the iron losses. So whatever the power consumption in OC test, that is nothing but the iron losses. So Pi is equal to 100 watt, and full load current on the HV side, I2 full load is equal to S upon V2. So S is 5 kVA, so 5 into 10 raised to 3 divided by 400 secondary voltage, that is in the short circuit short circuit test is performed on HV side, that is 400 is taken in the denominator, so it is 12.5. See here the full load current is 12.5, but in the short circuit test it is 11.4. It indicates that short circuit test is not performed at the rated load current. Hence the losses, which is the 200 watt here, it is not the full load copper loss. So we have to this 200 watt copper losses correspond to this current, not to this current. So we have to calculate full load copper loss corresponds to this current. So we know that the copper losses is equal to I2 square R2E. So copper losses is 200 watt corresponding to 11.4 current. Similarly, copper losses at full load is equal to I2 full load square into R2E, that is PCU full load 12.5 square into R2E. Taking the ratio of equation 2 to the equation 1, I can easily determine the copper losses as 240.45. So full load copper loss is equal to 240.45. Once you get this, we can calculate now efficiency. How to calculate the efficiency? For the efficiency, full load is given at 0.9 power factor. So n is equal to 1, power factor is cos phi is equal to 0.9. So using this formula once again, so which is given in previous problem, so n is equal to 1, cos phi is equal to 0.9, SFL is equal to 5 kVA, pi is equal to 1, n is also equal to 1, pi is equal to 100, n is equal to 1 square into 240.45. Here I am using the full load copper loss. So it gives you 92.96% efficiency. Now we want to determine the regulation. To determine the regulation, we need to calculate the parameter referred to the secondary side, and that can be calculated using the short circuit test. So short circuit test voltage and current is given. So from that, how we can calculate impedance? Impedance is equal to magnitude of impedance at an angle of phi. So VSC upon ISC. Wattmeter reading is W is equal to VI cos phi. So what is a cos phi? W upon VI. So what is a phi? Cos inverse of W upon VI. So angle is cos inverse of WSC divided by VSC into ISE. So VSC is 40, ISC is 11.4, WSC is 200. Again, substituting all this, I got impedance is equal to 3.509 at an angle of 63.98. Converting this polar quantity into rectangular, real part is the resistance and imaginary part is your reactance referred to the secondary. Once I get this R2E and X2E, and loading condition is full load current is 12.5 and power factor is 0.9, at which we want to calculate the regulation is to be calculated at these values. So I2FL into R2E cos phi plus X2E sin phi. Why I am taking it as a plus sign? Because it is for the lagging power factor. If it is leading, we have to take it as a minus. Okay. So first I will calculate cos phi is 0.9. So I will calculate sin phi is equal to 0.4359. So first calculate the phi, then take it as a sin phi. So it will get this value. So V2 is equal to 400 secondary side voltage. So 12.5, 1.539 into 0.9. So if you calculate this will give you your regulation as 8.62. This is the end of your electrical machines assignment. Thank you.